Okay, so this is a video that kind of piggybacks on the last one of the same title, as a function of, but this is more of the advanced stuff. The last one was more of the basics between two different equations that you could put together and find a common variable. Well, this one we're still trying to do the same thing, expressing a multivariate formula with a single variable, and we're going to really do that by finding the relationship here. So last one had a Pythagorean problem, a Pythagorean theorem, a squared plus b squared equals c squared relationship. These ones are going to be a little bit more advanced. Okay, they're all going to have, they're going to have proportional relationships. So let's delve right into this. So just like last time, we're going to give this problem situation. So here we have a cone with a vertex down. So let me draw that for you. So here's our cone with the vertex down. So there's the round part, the circular base, and then here's our cone with the vertex down. Okay, kind of like an ice cream cone, if you are so familiar with a sugar ice cream cone. Okay, it says it has a radius of 4, so let's put this information in there. Radius of 4 and a height of 8 feet. Okay, so a little bit larger than your normal standard ice cream cone, because these are in feet. So we want to express the volume of the cone as a function of just its height. Okay, so what we're going to do here is we're going to start off by writing down the volume for a cone. Volume formula is 1/3 area of the base, which is pi r squared, times height h. Okay, so if you were going to be given a problem in geometry, you could figure out what the volume is by using this formula for the volume of a cone. Sorry, that looks really ugly. Let me redo it. 1/3 pi r squared times h. So if we want to express the volume of a cone as a function of just its height, that means we have to somehow get rid of this radius variable. Okay, because right now the volume is a function of the radius and the height. We want it to be a function of just its height, so we can't have our r in there. Okay, so how are we going to get rid of r? And of course, last time we told you we get rid of it by substitution. So in order for us to substitute something into here, I have to figure out what r equals. I can't substitute without r being equal to something. So here is your secondary equation. Okay, you have to make up this relationship all on your own. You have to be able to see this. So within the cone, there is, of course, a right triangle. Okay, a right triangle made up of the maximum radius, the maximum height, and of course the slant height here of your cone as the hypotenuse. Okay, but there are also many more right triangles made up of different radii and different heights. So here is one, for example. Okay, this is when the radius is 2. And if we have a radius of 2 and this has to stay in proportion, that means I have a height of 4, and so on, and so forth. Okay, so there are lots and lots of different triangles in here. Okay, and this is true because both of these triangles, this largest one formed by our pink, okay, the maximum radius and the maximum height, is similar to any other right triangle within this. They both have a 90-degree angle, and they both share this common vertex angle down here. So by the angle-angle similarity postulate, both of these right triangles will be similar to each other. And whenever we have a similarity between two polygon, in this case triangles, your sides are going to be in proportion. So, and that's the key to doing this whole entire problem. There is a proportional relationship within every cone, okay, because it has a constantly slanted side here. We have proportional right triangles. So we have a relationship or a comparison between the radius and the height. Okay, there will always be this proportional relationship because these two right triangles are similar. So we set up this proportion, which is two equal ratios, the radius to the height. Okay, we're going to use its maximums. So the maximum radius is 4 when the maximum height is 8. Okay, so this is our secondary equation. This is the one we're going to solve for r, so that we can substitute it back over into here. Okay, so this is good for every single cone that you're ever going to see. There's always a proportional relationship between the radius and the height. So we set up and solve this proportion for r. So we cross multiply, 8r equals 4h, divide both sides by 8, and we get that the radius is reducing this 1/2 of the height. Okay, which makes sense. If we had a radius of 4, we have a height of 8, so the radius is half the height. If this is 2, that's 4, the radius is half of the height. So now that I know that, I can come back over here into my volume formula, 1/3 of pi times this thing that I want to substitute times h. So notice our radius is the height divided by 2. Okay, so looking at this equation, I just have h as my variable, and that's what it means to have something as a function of height, this h variable. No longer do we have two variables, we just have one variable. So now comes the algebra. Let's distribute this square. 1/3 pi h squared over 2 squared is 4 times h. So I have to multiply together all of these terms, my 1/3 term, my pi term, my h squared over 4 term, and my regular old h term. And how we do that is by multiplying fractions. So I'm going to turn all these things into fractions, h over 1, pi over 1. Everything can be divided by 1. And when we multiply fraction times fraction, you do numerator times numerators. So 1 times pi times h squared times h is pi h cubed. Okay, and all of my denominators, 3 times 1 times 4 times 1 is 12. So the volume of this cone as a function of its height has this as its equation. Pi times h cubed, the height cubed, divided by 12. So no matter what height I have, okay, if I know that this is 4 feet deep, I can plug a 4 into here and I can instantly calculate what that volume is. Okay, I don't need to know what the radial length is. Okay, this might be easy if I had to measure this. Okay, it's hard to measure a radius, especially when this is above ground. It's pretty easy to measure a height just with like a little window. Okay, so here's volume as a function of height. You always have a proportional relationship. That's where the second equation comes from. Okay, so here we have another problem, another nice geometric issue here, the triangular prism. So this prism has a base that's a triangle. So here's your base. By the way, there are two bases and they are parallel in this three-dimensional figure. So this is your base, which means your other base is over there. Has the dimensions shown. This is 6 and this is 2 here and that's 3. Express the volume of the prism as a function of its base height. Okay, so let's see. That means that's going to be this. This is your base height. This is your base base, I guess you could say, because it is a triangle. And this is your prism height. Okay, so it's important to be able to identify what these things mean. 3 is the height of your base, because our base is a triangle. 2 is the length of the base of your triangle, and 6 is the height of your prism. So when we start, we write down the formula, the volume for the prism. So the volume of the prism is area of the base times the height of the prism. So since our base is a triangle, 1/2 of base times height times, in this case, let's call this a capital H just to differentiate between our lowercase h, which goes with your base. Okay, so this goes here in our equation because this is a triangle. This comes from here because this is the height of your prism. Okay, the height of your prism is a distance in between your bases. Okay, so we want to write down this formula as a function of its base height. Okay, we want just h. So we need to get rid of this, and we need to get rid of this. Okay, this one's nice because it's always going to be 6. No matter what the level of water or food in this trough is, it's always going to be 6 units long. So that's a pretty easy one. We can do that. 1/2 of something times height times 6. Okay, so remember, this is all from your triangle. All of this stuff, 1/2 of base times height, comes from your triangular base that we colored here, where this height, this 6, is the height of your prism. So we need to figure out how the base relates to the height. Okay, so if you remember, this is a triangle. Okay, clearly you remember it's a triangle. But no matter what triangle I draw, so maybe that's the level of the water, maybe this is the level of the water, maybe that is, there's always going to be another right triangle here. Okay, so once again, these are all similar. Every single one of these equilateral triangles that we draw down here is going to be similar to the bigger one or the next one. Okay, which is great because once again we can set up a proportion. Because our triangles are similar, we can set up a proportion. So we compare any random base to any random height. Okay? So the maximum base length is 2 and the maximum height is 3. Okay, so we're always going to have this proportion of 2 base units for every 3 height units. Okay, the base will always be smaller than the height. So we solve this, of course, for, let's see, if we were trying to eliminate b, or rather get rid of b over there, that means we have to solve for b over here. So we're going to cross multiply. 3b's equals 2h's. Divide by 3. And 1 base is 2/3 of the height. Okay, that's good to know because that's what we're going to put over here. Instead of bases, I'm going to have 2h over 3. 1 base is 2/3 of the height. So if I had a height of 1, then the base is 2/3. If I had a height of 2, then the base is 4/3, and so on and so forth. So we could easily calculate any base length depending on the given height. So now that we know how the base relates to the height, I can simplify this equation. Let's see, 1 times 2h times h is 2h squared. 2 times 3 is 6. And then we still have our 6 on the outside. So now I can, this simplifies nicely. 2 height squareds. Okay, so that's how I'm going to find the volume of this specific trough as a function of its height. So the volume is 2 height squares. Okay, so we started with a general formula. We made it specific to this prism because it was a triangular prism. The triangle has an area of 1/2 of base times the height. And then we replaced the base with its equivalent over here. We set up this proportional relationship between the base and the height, using the maximum possible base and heights to figure out what that proportion is. We substituted, we simplified, and now we canceled out to get 2h squared over v. Okay, so sometimes these can be quite tricky, especially if you're not good at this algebra. But anytime we're dealing with a triangle, so here we have a triangular base. Here on this previous problem, this cone had some right triangles deep within inside there. There's always going to be a proportional relationship between your two variables. So you're able to solve and substitute by setting up and knowing that proportion. Okay, so hopefully this has been helpful, and you can go on and do all the other problems that you've ever had by using this information. All right, thank you. See you later.